So I love this conference so far because I actually don't even need to talk about this. Usually when I give this talk, I have to explain what's the deal with large surveys and why they're different. So I usually start very far back in history. So what's the deal with large surveys? We've been doing them forever by now. So one of the first ones was done by Hipparchus. He was actually a really clever guy. He discovered the precession of the equinoxes. He measured the length of the year to 6 minutes. This was all BC. And then in 1929 BC, he constructed one of the first star catalogs containing about 850 stars. He's also the one to blame for the magnitude system, by the way, so not everything about him is great. Now, this was the state of the art, or surveying the sky the way Hipparchus did was the state of the art, until Galileo came along almost 15 and 16 centuries later, and for the first time used the telescope to observe objects in the sky. So there's a common misconception that Galileo invented the telescope. He didn't. He was the first one to figure out how to do this. And since that happened, we've had this kind of a two-step interplay in astrophysics. So you would do a survey where you would construct a catalog or a map of objects in the sky. You focus on coarse classification and discovering the targets that are interesting for subsequent follow-up. And then you use large telescopes to acquire detailed observations of a few representative objects. Then you take that, understand the astrophysics, and extrapolate to the understanding of the entire class. So to give you an analogy with Google, something that we use every day, and something that uses us every day. Google search is sort of the ultimate survey of the internet, of the web. So Google's index is the catalog of the web. And we can write queries and then use it to zoom in on individual entries to find out. So in this case, I wrote a query, I typed in two-step. These are the top relevant links. I click on the first one, I get a link to Wikipedia, it tells me the two-step is a dance move. I click on the second one, I get a link to YouTube. It tells me that this guy knows how to do it really well, or at least well enough to garner more views than I'll ever garner on YouTube. And I can go and examine this topic by clicking on subsequent links, doing more in-depth research. So this really is sort of the analogy of what we've been doing in astronomy for a while. But there's an interesting thing that happens, that started happening as of the last few years ago, where if you type something like Dubrovnik weather into Google, you don't just get a bunch of links to different sites. You actually get a whole weather forecast. Because by now, Google itself has collected enough data and that it processes, it indexes, it visualizes, and it actually serves the information we need. So making the step of doing the in-depth, the subsequent more in-depth research, in some cases, not necessary. So more and more often, our research begins and ends with Google when you have large-scale data. Yes? Oh. Was there a question there? Okay. So I would argue that we're entering into the era of large massive sky surveys that are getting to the Google-ish scale when it comes to the sky. So there's a close parallel in here. We're entering the era where the scale is such that we can now image and catalog the entire sky repeatedly over and over again. The quality of those catalogs is now becoming as precise as the measurements taken with pointed observations only a few years ago. It used to be 5 to 10 times worse. Now we're pushing the quality to roughly the same level. And then the richness, and many people have pointed this out already, those catalogs not only contain positions of magnitude, but they contain information about shapes, about profiles, about temporal behavior of objects, much more information than we used to have. If you look at, for example, the SDSS catalog, you'll notice there are 400 columns describing every object. So quite often, again, not for every single use case in astronomy, but for a large number of use cases, our research can begin and end with the survey. And this is what makes large surveys of today and of tomorrow not just bigger, better, but different. They're much more than finding charts. So the challenge here for all of us and for the community is how do we make sure that the same things happens with surveys that happens with Google now? If we put in the right query, there's infrastructure, there's software behind it that will actually get you to the answer from the data that's already been collected. Now, this is a talk, this will be a talk largely about LSST, but I just want to point out you don't have to wait for 10 years to already start living in this world. We have already started pushing the boundaries into this sort of environment. And most prolific survey, if you're supposed to try with this today, is definitely SDSS, where from the SDSS data set that was originally built to do large-scale structure and cosmology, we've done so much different research. Now, very soon, this is a matter of weeks now, from what I understand, PanSTARRS is going to become public, and it's going to give us a few orders of magnitude, an order of magnitude more data than SDSS, over 3/4 of the sky, just kind of pushing that forward even more. And then finally, I shouldn't say finally, there will be many surveys in between, but what I'm going to focus on today is going to be the LSST. So LSST is the project that Jelko introduced 2 days ago that consists of an 8.4 meter telescope. It's going to image roughly half of the sky, very precise astrometry, photometry in 6 bands, very precise systematic photometry, and it will do this repeatedly over and over again for 10 years. It will cover the visible sky roughly every 3 days. We'll have about 1,000 visits for each point in the sky at the end of the mission. Each visit going down as deep as 24.5 in R band, and when you go out all of that, you get 27.5. So the way I like to think about LSST is, I think the tagline of this project should have been turning the sky into a database. Because that is what it will be doing. It will be imaging the sky, but processing in some way and putting it in a database. It will be an automated survey system. So in that time, the entire system will operate without human intervention. And the ultimate deliverable of the machine will not be the machine itself, the instruments. It will be the full reduced data. So for practical purposes, for all intents and purposes, if you're a user of LSST, this thing might as well be somewhere in space. Fortunately, it's not, so we can actually go and compare it to something that's pretty down. But all the science will be doing will come from survey capitals and images. The history of this project is interesting. It began decades ago, literally, as the dark matter telescope, a project to understand cosmology and the solar system. Because it turned out that you needed a roughly similar kind of machine to observe both the large-scale utilizing the Jurić and cosmology, as well as to discover the transitioning objects. What's happened around the year 2000 was that as more and more astronomers from different areas of astronomy got involved, they realized that roughly the same machine could do a lot for other areas as well. So then the focus was broadened as it was understood that we reached a point where a single telescope, a single general purpose data set can serve to answer wide swath of science questions. So Jelko showed a variant of these charts yesterday, that we have 4 different, to kind of bound the scope of the project, we defined 4 different science topics, or 4 frontiers of survey astronomy that LSST is supposed to cover. One is time-based science, and you know this, I think we decided a month ago in Caltech to just call it the Nancy plot. You know this plot, the Nancy plot, showing the characteristic time scale versus peak luminosity of various objects. The idea is that LSST will be able to fill in large swaths of this region that are currently unexplored. All kinds of novae, supernovae, European new objects that we don't know about. The ability to have instantaneous discovery. Next thing it's going to do will be a census of the solar system, discovering asteroids, discovering TNOs, discovering Oort clouds, potential cloud objects that we scattered inwards, comets, main belt objects, etc. Mapping the Milky Way. This piece, so what this is stellar number density in the Milky Way. The center of the Milky Way is up here. This circle around here is halfway to M31, so roughly 300 kiloparsecs. What you see here is actual data from SDSS. With LSST, you'll be able to push out to this inner circle using many sequence stars, and then all the way over this outer circle using entire light array. And what you're seeing here is simulation, and we hope to be able to make these kinds of images with LSST data, with real LSST data, in a matter of years after the machine begins. And finally, one of the big projects is dark energy, dark matter. So understanding this, specifically, especially concerning the nature of dark energy, is going to be one of the more interesting things that this telescope is going to do. And so I quickly ran through this because Jurić talked about it yesterday, but roughly this gives you an idea of what the goal is. And the goal is more or less everything that we have from the census of the solar system all the way out to dark energy. So it really is, let's image this file, let's put it in a database, let's enable all these kinds of science. Now, the status of the project, the machine is going to be down in Chile. The status is such that construction has already started. This here is a photo of the LSST site where the actual telescope is going to be taken on April 14th. These two telescopes are Japanese South and SOAR on the adjacent peak. This is what that site is going to look like in as little as 3 years. So we really expect this observatory to grow very rapidly right now. Jurić said yesterday we haven't been affected significantly by the recent quake. The mirror is done. It's all boxed up, packed in Tucson in a hangar where they apparently store really, really expensive jets as well. So it's kind of cool to have your mirror in a place where there are many, many more expensive things stored as well, and then you know that they'll care about it. The L16 camera is in the process of being in production. It's in the process of being produced, 3.2 megapixels, 10 square degrees field of view. And once all this hardware is built and integrated and deployed, I think that the number one challenge for this machine will be processing the data in a way that enables science effectively. So to give you an idea why I say that, this is going to be a 3.2 gigapixel camera. It's going to be taking 2,000 images every night. So when you add in calibration data and so forth, that's about 15 terabytes of data per night. We want to do things like real-time transient detection. We want to do things like COAPs. We want to do things like discovering asteroids. We want to do all of this all the time. There's no way we can do this manually. It has to be automated. There are going to be catalogs on orders of 40 billion objects. There are going to be trillions of observations. So making sure that you have a way to process the data and the software to do it automatically, I think, is the number one challenge, and especially for something of this scale. So how do we do that? One of the things that LSST is going to do, in addition to that, one of the unique properties of LSST compared to prior experiments in optical astronomy, is that it's going to be a fantastically well-characterized machine. So we will know, or we're designing it so that we know a priori the details of the optical system, the details of the behavior of the camera, that we can predict and characterize so many things that effects that you would usually sweep under the rug when you're doing processing in LSST can actually be measured and corrected. So how do you take those effects and make sure that you use them properly when you're processing the data? On the other hand, you have a problem of how do you make that data processing process tractable and understandable. So if we go back to the beginnings, or to the basics, let's say I collect some images and I want to test the hypothesis or the theory that I have. Right? What I would do, if I had all the knowledge in the world and all the theory in the world, is I would have my model. For example, if I care about galaxy shapes, I would posit that galaxies have certain parametric form that describes them, and then I would go and fit that model directly to the data, taking into account everything I know about how these images form. I would do that simultaneously for absolutely everything for the entire survey, and that really is the optimal. I would use correct priors for what I already know from previous surveys or from theory, and that really is the optimal way to extract information from the survey and add it to the knowledge about the model. Now, the issue with that, of course, is that that is tremendously computationally expensive. It's science case specific. But what I think is the most important bit is that it's cognitively expensive. So you need to understand everything there is to know about the telescope, about the data, about calibrating it to get this done. And very few people can do that. I'd say no single person can do that. So what we typically do when we do our surveys is we break up this inference process into a couple of additional steps. So instead of going directly from model to the data, what we're doing is we introduce these data processing steps in between. So you take your data, you do some processing, and typically you reduce it down to a catalog. If you were talking about with the CMB, you would reduce it down to maps. If we're talking about radio sky, visibilities, and so on. And the thing with that is that then this bit here, taking the data and turning it into a catalog, that is where the computationally expensive part is. But that is something that if you think a little bit about how you do it, can be made general. What this is, when you think about converting data to catalogs, this is really a reprojection. So we talked, somebody mentioned that yesterday, the day before. In effect, what we're doing is we're taking data that's in the space of pixels, reprojecting it in another space, in this case, the space of objects in the sky, that is more understandable to us. Now, I'd say may or may not involve compression. Typically, decades ago, if we had images, you got a catalog out there. The catalog for each object would have only a few entries. Therefore, it would be a fantastic way to really do compression, because you go from megabytes of pixels into a few entries. These days, that's not really true. In fact, for LSST, we're going to measure so many different quantities on virtual every detection that the catalogs are actually going to be bigger than the imaging itself. You're not going to be using all of it all the time, but they will be bigger. But almost always, this introduces some information loss. One simple example, you use information about the background noise. I mean, we don't think about the noise as information, but information derived from that actually is information. You lose information about what the noise is doing. More importantly, if you're doing source extraction, you use information about what's going on with diffuse sources. So that's one example. And this data processing incorporates all of our knowledge of instrumental calibration and of ways we do measurement. So this is where you get all your experts who know about the telescope, about the instrument itself, about calibrating it, work into this step to produce the catalogs that are minimal calibrated. Now, once you have catalogs, you give catalogs to models. This is computationally cheaper, significantly computationally cheaper. This is much easier to understand for an average astronomer. It's much easier to work in space of objects than it is in space of pixels. And then this can be made science case specific. So this here can be made roughly in general, then your science case specific bits go in here. So this is a way, one other thing is, if you do this, then the project collects the data, the scientists do everything else. If you do that, then the project does all the processing to a catalog level, and then science begins here. Now, if you think that this is silly, that it actually isn't, because that's what happens today at observatories, where you go and take your images at an observatory, you take them home and do all your processing yourself. This here is what's already happening in large surveys. So the way to think about data and data processing in big surveys, really, the way I think about it is as a generalized cost reduction tool. So if we could do this, if we had infinite resources, I think we would always be doing this. Because we have infinite resources, we don't care. But we need to reduce costs, not only in terms of dollars, but in terms of brain power. Because doing this is hard. So I think catalog generation is really a generalized cost reduction tool. And the issue is you want to make that catalog generic enough so that you can have most science cases use it. So how do you do that? If you think about it this way, then I think guiding principles become easier to define. So for large surveys, the things you want to do is you want to maximize the science enabled by the catalogs. So it sounds like an obvious statement, but it leads to some slightly non-obvious conclusions. This is one that I'd like to emphasize. For example, we may know of better ways to measure things in data, analysis theory data, but we will still be including things like Petrosian magnitudes or chrome magnitudes. And partly because that is what people are used to doing. So if you want to enable a smooth transition from what's happening today to better methods of the future, you need to keep including that, let's call it backwards compatibility layer into your calendars as well. Minimize information loss is another one. So you want to try as much as possible to record as much information you can about the object and in such a way that if the person chooses to use it, they can. If they don't choose to use it, they don't have to. So one of the things that we will be doing is instead of just providing maximum likelihood estimators for virtually every quantity in the catalog, we're going to be recording likelihood services. If you care about systematic limited problems where you really need likelihood services, you can use it. If you don't have to. And then finally, provide and document transformation to the software itself. These measurements are becoming increasingly complex and systematics limited. So to understand really what's going on, you need to be maximally transparent about how the measurements are done. And that means giving the software in the end. So I think many of the surveys today, it's very hard to penetrate what was measured. It might say Petrosian magnitude, but you don't really know how that's being done. And that's something that at these scales we're going to start caring about. So this is, once you take that into account, this is what LSST is going to look like from the user's point of view. It's going to be a stream of about 10 million time domain events per night. This is what we call level 1. These are, this is nightly data that's been designed to enable rapid follow-up. So every time a telescope observes a certain area in the sky, we rapidly difference that against per template, and within 60 seconds, we detect everything that's changed, and we want to transmit that out to the lower distribution networks to enable follow-up. On a yearly time scale, we're going to do data release processing. This is very analogous to what SDSS did, or what PanSearch is doing right now, or what WISE does, or Split, or Galaxy, or any other survey. This will happen on yearly cadence. All data from the beginning of the survey will be processed with a single consistent version of the software to make sure that we have a self-consistent data release. And finally, there's going to be this edition, which is somewhat new, where we'll enable people to do two things. One is to bring their computation to the data, and the other, which I actually find more interesting, is we're going to open up all the source code and make it easy for people to set up their own data processing and add their modifications, set up their own data processing runs whenever they have to. So both parts are here. So we're talking about development in a little bit. What's going to be included in level 1, I already mentioned about how it's going to be generated, but with each alert, we're going to be measuring positions. We're going to be measuring a few different fluxes, a KSET flux, aperture flux, and a few different apertures. We're going to be making trail model fits, so this is very useful for things like moving objects, asteroids. We'll measure shapes through depth moments. We will automatically match any detected objects to previously detected objects at the same point in the sky, thus constructing light curves in real time, computing some variability characterization information in those light curves. Right now we're baselining on Jurić et al. For the features we're going to extract, but to be honest, this is really a placeholder. This is going to be an area of active research and discussion with the community. What's best, what features are really best to compute. And we're going to look at blank screens, cutouts centered on the object, both in template and in the image. So all of this will be happening in real time, and roughly within that 60-second period. All of that we want to package into an alert packet and send it out. So that someone downstream who's deciding whether this is interesting or not has all this information essentially 60 seconds after the observation has ended and is able to make a decision what they want to do with it. On an annual time scale, this is the kind of processing that's going to be done. So object characterization, multiple fits of multiple models in different ways. So moving point source models, so we'll fix each object in multi-epoch fashion as if it was moving to detect things such as stars with measurable proper motions. For galaxies, double Sircig, both this models, many non-parametric characterization measures, colors, and variability statistics. So for each object, we're going to compute variability statistics, essentially the same ones as here, but with somewhat better photometry, because now we have more time. We don't have that 60-second deadline. And you don't have to actually take photographs of these slides, because all of this is explained in a document called the Data Files Definition Document. If you go to ls.st/dpgd, you will find it. Level 1, 2, and 3 data products are described in there. And the thing that I would want to stress here is that this is a living document. So this is something that we keep updating and keep refining as we're going through construction to make sure that this is exactly the thing that is going to enable science and that it's relevant when we start. So I would actually ask you to read this, and then if you have any questions, post them on community.lcc.org, or if you really know what needs to be changed, or think that you really know what needs to be changed, and would like to propose a change, you can actually go and execute a pull request on GitHub. This document lives on GitHub, and that is actually the way we update it. It's just a LaTeX document. So the point here is that we're trying to get the community involved as much as possible to make sure that the analysis teams on the sky delivers what the community needs. Okay, so let's stop talking a little bit about LSST and look ahead and talk about data processing in general in about 10 years. And I'm going to start, because otherwise it will be boring, I'm going to start by making a few controversial statements. The first one is going to be that so far, I think, much of astronomy and astronomical software has been a lesson in intelligent cutting of corners. So I would say that so far, compared to certain other areas of science, we really didn't need particularly sophisticated codes. And I'm going to claim that we were lucky in that. I'm going to claim that that's actually great. Because A, there was no data. That's a little bit less great. B, if there was data, data wasn't that good that you needed sophisticated software to go and do something about it. Or C, even if there was good data, you usually didn't have enough computing power to do the right thing. And more often than not, you had all of the above. So from the point of view of astronomical software, life was easy, because simple algorithms were sufficient. The challenge was in the hardware. So from the point of view of someone having, a bag with, let's say, $100 million, it paid more to give it to the hardware person to go build a bigger and better telescope or a more better characterized instrument than to a software person to try to extract more information from already crafted data. Now I'm going to make an argument that this is fundamentally changing. That astronomy is becoming software bound. Right now, already, so just forget about LSST. Look at the projects that are on the sky right now. Look at things like Catalina. Look at things like PTF or ZTF very soon. We can collect, or CANSTARS, we can collect amazing quantities of data. And those telescopes and cameras that are being built today are now extremely well characterized and calibrated. So it's not just that you're collecting amazing quantities of data. You actually have all the information to measure them really, really precisely. And computing has reached a level where you can actually do that, where you can throw complex algorithms at the problems and expect them to finish in Hubble time. The computing is also getting cheap, which is another important bit here. And also, if you look at how computing is evolving, right now, you may have noticed that the machine that you have, your desktop, is roughly running at the same gigahertz, same number of gigahertz as it did a decade ago. And just what's increasing is the number of cores. What you notice less is that there's an even worse trend going on with memory. So bandwidth to memory, although we're getting more and more memory, the bandwidth to memory is actually, it's not quite constant, but it's definitely not exponential. So what's happening now is Moore's law still works with cores, with increasing number of cores on the CPU level, but Moore's law stopped working on the level of memory bandwidths, which means that now you have more and more cycles per byte of data to spend, which means that you're actually being pushed by this cheap computing into devising more and more complex algorithms. So you take an image, you better come up with something really complicated for it to do, because otherwise this new computer that you just bought won't be that much better than the previous computer, because you're going to be bandwidth limited. And the final piece that's changing today is really that now science has started requiring better algorithms, better software, because we've maxed out on the build a bigger telescope part. So LSST is going to cost more than $1 billion in the end when you take operating units account. If you think about what you're going to do next, and whether you invest into improving software for LSST or something else, the answer is software, because the next thing is going to cost a few $1 billion if you want to go bigger. And it's hard to imagine software costing that much when you rate it right, or when you weight it right and improvements you get. So I think we're getting and the final point is that now the time to develop that software is actually becoming greater than the time to build the astronomical hardware. So the point here being is that we are becoming software bound, algorithms bound. So in LSST, we feel that really strongly because of the nature of the project, we have to build all of these pipelines. And if you look at these, if you look at what's written here, it's essentially a combination of SDSS, what SDSS has, what Catalina has, what PTF has, all put into one and the same machine. I think the closest to this today is probably CANSTARS. And we also, because we are in the area where this telescope is already fairly expensive, and you want to build, and building a bigger one is infeasible, we want to make sure that this processing is done as optimally as possible. So one example of that is multi-epoch measurement. I'm going to just run through this very quickly, because what multi-epoch measurement means is how do you characterize data, or sorry, how do you characterize objects in the image if you have multiple images. Typical way we do this is by building a collab. That is really not something that you should do. So this part is computationally hard, and this part that's easy, but this is really the point. This is something that we shouldn't do because it loses information. So for example, it's impossible to combine multi-epoch data taking different scenes or exposure times without information loss. You get suboptimal noise in the end. warping and resampling, when you do that combination correlates pixel values and noise. You cannot carry that forward, so you get an additional source of systematic error that you may or may not be able to tease out with Monte Carlo simulations, but then you need to make sure that you have those simulations. Detector effects, they have to be taken out at the pixel. There are detector effects that if you do coads, you have to take them out at the pixel level. You further correlate the noise, make things more difficult. The effective band passes themselves change from exposure to exposure. If you care about things at a sub-percent level, then that makes a difference because you're starting to add different kinds of apples when you add two images, because it's not really R-band, it's R-band with that time of night, R-band and some different time of night. So the final thing is that stars move. So if you're trying to, for example, characterize a star by making a deeper coed image over 10 years, you may discover that on a coed you have a little galaxy because the stars are moving. So what you really want to do is you want to fit simultaneously to all the epochs. And so now your diagram, your flowchart turns into something like this. This is what we're actually going to be doing. But now note that we have, instead of one epoch, instead of one coed onto which to fit, we have hundreds, and actually thousands at the end. So we're going to have 1,000 images onto which you're fitting. And so that's where you see that decreased requirement on data processing. And the second thing that is important is with these model transformations, you really need to understand the PSF, the detector effects, everything that's gone into an individual image, which means that the requirements on calibration of the telescope are much higher. But I just told you the telescopes we're building today are up at that level of precision. So you actually can do this both because now you have computing and you have this characterization of the instrument. So we're going to be doing things like this. Another thing that enables you to do is I mentioned stars that move. So here's an example from Dustin Lang's paper. It's going to come up in a second. Where he shows an example of a simulated star that in each individual epoch is below the 5 sigma detection threshold that's been adopted here. But when you actually go and fit the position and proper motion of this star simultaneously and parallax, you recover it pretty well. So this is what he's getting after the simultaneous fit. If you just did a naive coad, you would get something that looks like this, that's extended. And then, because you actually wouldn't detect it in individual images, you might think that this is a galaxy and then contaminate your galaxy sample, which may or may not be important depending on what you care about. And you would definitely lose information about the proper motions of stars at this level. And the final thing I want to show you and to kind of demonstrate how these algorithms are moving forward and becoming more the data outputs are becoming more rich are these likelihood distributions. So I already mentioned that for every parameter, we're trying not to just record maximum likelihood values, but report full exteriors. So on top of having to do this now for 1,000 more exposures than we ordinarily would, we'll actually multiply that by an order of 200 because we want to measure samples out of the likelihood distributions. So it is becoming a bigger computational problem, but it will lead to more science. Now, just a few more slides at the end to actually claim that we can do even better, that we can do much better than that conceptually in other ways. So I've shown you this just a second ago and said that this here is horribly complicated, and it is. But as our measurements become more and more systematic limited, what occurs in this data processing box becomes incredibly important. And sometimes an assumption or an algorithm choice that's been made there may introduce systematic bounce out of the signal or even eliminates it. So somebody else is doing data processing for you. And so here are a couple of examples. We're going to be using some blending algorithm. That algorithm is almost certainly not going to be optimal for everything because you have to make many assumptions on how to do the blending. You may want to choose your own algorithm. Practical photometry. If you care about photometry of stars and these kinds of objects, it's very hard to imagine that the survey project is going to deliver the optimal thing for you. These things you won't detect at all. So these are supernova light echoes. You won't see the catalog of these. You're going to have to do it yourself. Diffuse structures. I mentioned that a couple of days ago. We have no plans to make a catalog of diffuse structures. So there are going to be many, many things that are either absent from this catalog or are not potentially measured in the way you care about. And for optimal inference, this is a general statement. One wants to design measurements that directly probe relevant aspects of that original imaging data and not the lossy compressed catalog. So we don't do this today for reasons that I already mentioned. It's computationally expensive and conceptually difficult. But things are changing there as well. So big problems are now becoming increasingly computationally practical. And I said this is cognitively difficult, but I mean the students we're educating today are actually growing up with an expectation of being well-versed in all they need to start doing these kinds of problems, including understanding instrumentation. And the third, I think, most difficult part is software. So if you want to do this yourself, what you would want to do is to use components, 99% of what the survey has been doing here, and just plug in your piece that's different or your piece that's missing. That's been impossible to do so far. But that is changing. It's primarily being driven by people in few large survey projects and large telescope projects. But it really is changing. So I think in 2025, astronomy is going to be like personalized medicine, or astronomy software is going to be like personalized medicine. You're going to have the base software stack out there, and then you're going to go and modify it to do the things that you care about. And with our level 3 concept, we're doing the first step in that direction. So we're going to be providing all those software primitives to construct custom measurement inference codes and to enable users to run those either at the LSC data center or actually elsewhere. You should be able to just spin up a cluster with 100,000 cores on Amazon and just go at it. And looking ahead, I actually think that by the time we're done in the 2030s, this is what might be the legacy of LSST and projects that are going to be running at the same time. It's not going to be the data release, it's going to be the software that enables others to create specialized catalogs, specialized processing, specialized data releases. And in that case, data releases from surveys are going to be just some of those catalogs. And their defining quality or characteristics are going to be they're going to be designed to be more broadly useful than others or retained for a longer period of time. And so one of the key things that we're trying to do when we're thinking about LSST software is to engineer it and hardware, to engineer it to make this possible. So that you have, in essence, an analysis pipeline in a data center in a box. You can go and deploy it, you can go and change things, and run your custom analyses as you see fit. Once you get to the point where catalogs are not enough. And for certain kinds of science cases, that point is likely to be reached. So for things such as simultaneous processing of LSST data, the first data, Euclid data, where we really care about all kinds of systematics, I think you will want to go back to the process. And so I will end with this slide. Traditionally, where data started science, we aren't anymore. Traditionally, it paid to throw more money into hardware. Now I think we're at a point where we need to throw money into software. That the environment, in this environment, success in research will depend on ability to mine knowledge from that data. And a bigger instrument is not a cost-effective solution anymore. And I tease my dark energy friends that maybe a stage 5 DETF experiment will be done in software, not in hardware. And I think for this audience, this is kind of my opinion where things are going. I think this will reignite the drive behind VO like it is. I think the emphasis will shift more from standards and interoperability to algorithms, tools, and reusable collaborative software frameworks. So I think projects like AstroPy are particularly driving that forcefully and I think in the right direction. I think AstroPy has shown how it's possible to grow a community of 200 astronomers working on a software package. And I think LSST is pushing on this as well, in the sense that while AstroPy is more oriented towards basic analysis components, LSST is oriented towards creating state-of-the-art algorithms and making it possible for people to use them. So that is a great, and not just making it possible, making it supported. And my final point is that I think necessity is the mother of all invention, right? And as long as we didn't need to do these kinds of things, as long as we don't need to do them, they won't get done, because it's better to spend energy elsewhere. I think we're coming to a point where necessity is here, and invention is going to